Have you ever just, stopped and thought about how we experience time and space? We kind of treat them like they're fixed, right? Unchanging. But what if I told you they're not? Today, we are diving headfirst into one of the most mind-bending, reality-warping ideas in all of science, the theory of relativity. And trust me, it's a story that starts with a super simple question and ends up rewriting the rulebook for the entire universe. So let's get into it. All right, let's kick things off with a little thought experiment. I want you to picture this. You're on a super sleek, high-speed train. The ride is impossibly smooth, but all the window blinds are down, so you can't see a thing outside. Now, without peeking, can you really tell if you're standing perfectly still at the station or if you're blasting down the tracks at 200 miles an hour?
Now, you might think this idea of relativity is some wild, modern concept, but what's so fascinating is that it's actually been around for centuries. We're talking Galileo, Newton. These guys were thinking about this stuff a long, long time ago. And the best part? It's a kind of relativity that just feels, well, totally intuitive to us.
Back on that train, think about it. Everything feels completely normal. You could pour yourself a drink and the liquid would go straight into the cup. No problem. You could even play a game of pool, and the balls would roll and bounce exactly like they would on solid ground. So here's the key. As long as your speed is constant, the laws of physics behave in exactly the same way. You just can't tell you're moving.
And of course, physicists have a name for this. It's called an inertial frame of reference. It's basically any situation where you're not accelerating. So that means you're either standing still or you're moving at a perfectly steady speed in a straight line. In any of these inertial frames, all the basic rules of physics, like F equals ma, they work perfectly. So you on the train and someone standing on the platform, you're both in your own equally valid inertial frames. And this is where the crucial difference is. A constant, uniform speed is totally relative. You honestly can't feel it without some outside reference point. But acceleration? Oh yeah, you can feel that. That's absolute. If that train suddenly lurches forward or slams on the brakes, you feel it. You get thrown back in your seat or pushed forward. There is zero doubt when you're accelerating. So for about 300 years, this version of relativity was a bedrock of physics. It made sense, it worked, everything was great. But then, in the 19th century, a new character entered the story that was going to throw a massive wrench in the works. And that character was light. So you had brilliant scientists like James Clerk Maxwell, and they were digging into the mysteries of electricity and magnetism. And buried deep inside their equations, they found something just astonishing. It was a prediction that light was a wave and that it traveled at this incredibly specific speed, 300 million meters per second. This wasn't just some random number. It looked like a fundamental constant of the universe itself, a cosmic speed limit we now call c.
But hang on a second. That created a huge puzzle. A speed has to be measured relative to something, right? I mean, sound waves have a speed relative to the air they're moving through. So what was light moving through?
Well, to try and solve this, scientists came up with this idea of a mysterious, invisible substance they called the luminiferous ether. They imagined it filled every single nook and cranny of the universe. The problem was, this ether had to have some seriously weird properties. On one hand, it had to be more rigid than steel for light to travel so fast, but on the other, it had to be completely and utterly frictionless so that planets could just glide through it for billions of years without ever slowing down. It was a bit of a stretch, but it seemed like the only game in town.
Okay, so if this ether exists, the next logical step is pretty obvious. Let's try to measure how fast our planet Earth is moving through it. But when scientists actually tried to do this, they found something so bizarre, so completely against all common sense, that it basically broke physics.
I mean, just think about it from a common sense perspective. Speeds add and subtract, right? If you're running towards someone who throws a ball at you, that ball is going to seem like it's coming at you faster. If you're running away, it'll seem slower. This is basic Galilean relativity, and it works for everything. So it should work for light too, shouldn't it? So the logic behind the famous Michelson-Morley experiment was dead simple. Step 1. The Earth is zipping around the sun, so it has to be moving through this ether at some speed. Let's call that speed v. Step 2. A beam of light travels through that same ether at speed c. So step 3, if we shoot a beam of light in the same direction the Earth is moving, we should measure its speed as c minus v, because we're kind of catching up to it. Makes sense. But when they did the experiment, the answer they got was just impossible. It didn't matter which way they pointed their device. It didn't matter if it was day or night, summer or winter. The measured speed of light was always exactly c. It was like the Earth wasn't moving at all. And then, to make it even crazier, They waited 6 months for the Earth to be on the other side of the Sun, moving in the complete opposite direction, and they got the exact same result.
This wasn't just a little measurement error. This was a full-blown catastrophe. The entire world of physics was in crisis. You had two ideas that were in direct, violent opposition. On one side, you have the common-sense rules of motion. On the other, you have the weird properties of light. Both couldn't be right. Something had to give.
And this is where a young 26-year-old patent clerk named Albert Einstein steps onto the stage. And his solution wasn't just a minor tweak. It was breathtakingly simple, and at the same time, unbelievably radical. He didn't try to fix the old rules. He just threw them out and wrote two new ones.
See, Einstein's true genius was this deep, unwavering faith he had that the laws of nature should be elegant and consistent. He thought, look, if the principle of relativity works when you're playing pool on a train, it has to work for everything, including light. He realized that if the speed of light wasn't constant, you could use that to tell if you were moving. And to Einstein, that felt like a cheat. He just believed the universe wouldn't be that messy.
So he laid down two new fundamental principles, his two postulates. First, the principle of relativity applies to all the laws of physics, not just motion. That includes electricity, magnetism, the whole shebang. And second, that crazy, impossible result from the Michelson-Morley experiment, that wasn't a mistake. It's a fundamental law of nature. The speed of light is the same for everybody, always, no exceptions.
Now here's where you need to buckle up, because if you accept those two postulates as true, and they are, you are forced to a conclusion that is so bizarre it shatters our entire perception of reality. You have to give up on the idea that space and time are absolute.
Just think about the math for a second. Speed equals distance divided by time. So, if two people are moving relative to each other, but they both have to measure the speed of a light game as being the exact same number, then something else in that equation has to change to make it work. And what's left? Distance and time.
And this is the part that blows your mind. Einstein's theory proves that for the speed of light to be constant for everyone, our measurements of space and time must be relative. This means people moving at different speeds will literally experience time and space differently. A clock that's moving fast relative to you will actually appear to tick slower than yours. A ruler will appear to be shorter. And this isn't some trick of the eye, it's real.
This just completely demolishes the old-school Newtonian view of the universe. In that world, space and time were absolute. They were like a rigid, unchanging stage where the events of the universe played out. But at Einstein's universe, no way. Space and time aren't separate things at all. They're woven together into this single, four-dimensional fabric called space-time. And that fabric isn't rigid, it's dynamic and flexible.
And really, that's the absolute core of it all. Einstein's great revolution was realizing that space and time aren't this fixed backdrop. No, they are active participants in the universe. They will literally stretch and shrink, they will warp and bend, doing whatever it takes to make absolutely sure that every single person, no matter how they're moving, measures the speed of light to be the exact same.
This idea just fundamentally rewired our understanding of reality, and it leaves us with this incredible question to chew on. If something as fundamental as the passage of time itself depends on your motion, what other things in our lives that we take for granted as being absolute and fixed are really just a matter of perspective?